The SQL Handbook. Information Systems. Data and Information. What is a database? And a DBMS. Do you always need a database? Relational databases. Introduction to SQL. Creating a table. Inserting data into a table. Querying data. Handling empty cell. Unique and primary keys. Update data on the table. Update the table structure. Deleting data on tables. Joins. Removing duplicates and using distinct. Using wildcards with like. Indexes. Aggregating data. Grouping data. Limit and offset. Comments. The goal of this handbook is to get you up and running with SQL, starting from zero knowledge. You will learn the terms and the main IDs. What is a DBMS? How to structure a database? How to insert data into it? How to query the database? I will only teach you the basics. And once you're done with this, you'll have the knowledge you need to dive deeper. I called this SQL Handbook, but I assume zero database knowledge. So I'm first going to give you an introduction to databases, in particular relational databases. Point 1. Information systems, data and information. The modern world is completely centered around information and data. What's the difference between information and data? Data is a singular unit of knowledge. It has no intrinsic value on its own. We can't extract meaning out of it without knowing more about it. Information is something that we can link to data to be able to attach a meaning to it. Let me make an example. The number 36 is data. Knowing that 36 is the age of Joe is information. Information that the data represents the age is essential knowledge that is key in an information system. Point 2. What is a database and a DBMS? A database is a collection of information carefully organized into a system. The technology that in a computer system lets us organize data and represent the information that is essential for an information system is called Database Management System, DBMS. A DBMS is a software that encapsulates the data of a database and provides us a way to store it, retrieve it, edit it, persist it, and much more. We ask a DBMS to be efficient, to privately and securely store data, to handle large amounts of data. Point 3. Do you always need a database? Do you always need a database for your app? Of course not. Many times you don't even need to store data. But if you need to store data, you have various solutions. As with everything in technology, nothing is ideal in every situation. Computers offer many various ways to store data. The most obvious alternative is files. A common example is a website. Some websites use a database to store data, like WordPress. Some do not. Not using a database in that case means a simpler deploy to a hosting service, since you won't need to use and maintain a database in the first place. But when handling lots of data, a database is definitely a great way to simplify your life in the long term. As always, it's all a balance of complexity versus convenience. Point 4. Relational databases. We have many different kinds of DBMS. Computer professionals experimented with many different options in the past, and one of these options got very popular, the Relational Database Management System, RDBMS. For simplicity, we generally call them relational databases. You might have heard of postgresql, mysql, Oracle, SQLite, MariaDB, SQL Server. Those are all relational databases. Note the SQL in their name. They are also called SQL databases. To contrast, NoSQL databases like MongoDB or DynamoDB, for example, which are DBMS that do not use this relational model and do not use SQL as their language. Relational databases under the hood organize data using two simple concepts, tables and relations. This makes them very intuitive to use. Because we are used to using tables, to organize them. Think about an Excel or Google Sheets. For example, a relational database at the first glance is similar. Data is stored in one or more tables. A table is a collection of items organized in rows and columns, like a name and age. Each table contains one or more columns that hold data of a specific type, like strings, numbers, and so on. The set of a table and all the rules about its columns, like the type of data stored, is called a schema. Each table can define constraints upon the data that each row can contain. For example, in the simplest case, we can say that the value of a column cannot be empty. Tables can reference each other, forming relationships. For example, we can say the row of the car table with ID 1 is owned by the user assigned to ID 2 in the table users. In this way, we can link data together and build more complex applications. Relational databases offer us, users, the ability to interact with them through the SQL language. It looks like this: select pointer from cars, insert into cars values, parenthesis Lamborghini, 2010. We use this language to define the table's schema, fill tables with data, and finally curate the data when needed. The rest of this handbook will be focused on SQL. SQL is rather old, being born in 1986, and it's a battle-tested technology used in all sorts of applications. Point 5. Introduction to SQL. SQL, Structured Query Language, is a language we use to interact with a database management system, dbms, to exchange information with it in a standardized way. As the name suggests, it's not a programming language, but it was born as a querying language and later evolved to an interface to doing more advanced operations with the database than just performing queries. I said evolved, but in reality SQL is always evolving. It's a standard that was first published in 1986, then updated in 1989, 1992, 1999, 2003, 2006, 2008, 2011, 2016, and as its latest version, 2019. SQL is implemented in many popular DBMS, Postgres, mysql, Oracle, SQLite, Microsoft SQL Server, and many more. Each different database implements a standard or a particular version of it and adds custom features on top of it. To simplify curating queries or adding a specific functionality, SQL is a huge subject, and you can literally spend years to master all its features. And this handbook will only cover the basics to get you up and running. I recommend you try running the SQL I explain in an online playground experimenting tool like dbfiddle or similar. A great application to run SQL locally on your own database is TablePlus. As a developer in your applications in your day-to-day, you might use an ORM, Object Relational Mapping, library that abstracts SQL and simplifies your life. But it's absolutely essential to know how things work under the hood. And much of the terminology of ORMs reflects the underlying SQL naming conventions. Plus, some things are just doable using plain SQL. So let's go. Point 6. Creating a table. A database is composed by one or more tables. Creating a table in SQL is done using the create table command. At creation time, you need to specify the table columns, names, and the type of data they are going to hold. SQL defines several kinds of data. The most important and the ones you'll see more often are char, varchar, date, time, datetime, timestamp. Numeric types include small int, integer, decimal, float. Those above all hold numbers. What changes is the size that this number can be. Consult the manual of your dbms to see exact values, because this is one of the implementation details that can change. Also, each dbms can introduce non-standard types like begins or a tiny int or text, and even advanced ones like JSON or array types. You can absolutely use those, as long as you know that switching dbms to a different one, say from postgresql to SQL could be problematic if those non-standard types and features are used. This is a syntax to create a people table with two columns, one an integer and the other a variable length string. Create table people parentheses hint, name varchar parentheses 20. Point 7. Inserting data into a table. Once you have a table, you can insert data into it. Take this table. Create table people parentheses hint varchar parentheses 20. You can now start adding data into it with the insert into command. Insert into people values 37 Joe. You can insert multiple items, separating each one with a comma. Insert into people values 37 Joe. 8 Ruby. Querying data. Point 8. You can get data out of tables using the select command. Get all rows and columns. Select pointer from people. Age name age 37. Name Joe. Age 8. Name Ruby. Get only the name column. Select name from people. Name Joe Ruby. Count the items in the table. Select count pointer from people. Count 2. You can filter rows in the table adding the where clause. Select age from people where name is Joe. Age 37. The results of a query can be ordered by column value, ascending, the default, or descending using order bar. Select pointer from people, order by name. Select pointer from people, order by name. DESC. Point 9. Handling empty cell. When you create a table in this way, create table people age and name varchar 20. SQL freely accepts the empty values as records. And to insert into people values null. This might be a problem because now we have a row with null values. Age name age 37 name Joe, age 8 name Ruby. To solve this, we can declare constraints on our table rows. Not null prevents null values. Create table people age int not null, name varchar 20 not null. If we try to execute this query again, insert into people values null, we'd get an error like this. Error. Null value in column age violates not null constraint. Detail. Failing row contains null. Note that an empty string is a valid null value. Point 10. Unique and primary keys. With the table created with this command, create table people age int not null, name varchar 20 not null. We can insert an item more than once, and in particular we can have columns that repeat the same value. We can force a column to have only unique values using the unique key constraint. Create table people parentheses age int not null, name varchar 20 not null unique. Now if we try to add the Joe twice, insert into people values 37, Joe, semicolon. Insert into people values 20, Joe, semicolon. You'd get an error. Error, duplicate key value violates unique constraint. People name key. Detail key name as Joe already exists. A primary key is a unique key that has another property. It's the primary way we identify a row in the table. Create table people and int not null. Name varchar 20 not null. primary key. The primary key can be an email in the list of users. For example, the primary key can be a unique ID that we assign to each record automatically. Whatever that value is, we know we can use it to reference a row in the table. Point 11, update data in the table. The data stored in the table can be updated using the update command. Update people set ages to where name is Ruby. It's important to add the where clause. Otherwise, this instruction update people set ages to will update all rows in the table. Point 12, update the table structure. We can alter the existing table structure using the alter table command, followed by the alteration you want to make. Alter table people add column born year int. This will add a new column with empty values. Age, name, born year. Drop column alter table people drop column born year. This will result in age name 37, age name 8 Ruby. 13. Deleting data in tables. To remove data from a table, use the delete from command. This deletes all rows. Delete from people. You can use the where clause to only remove specific rows. Delete from people where name Joe. To delete the table instead of the data inside the table, use the drop table command. Drop table people semicolon. Point 14, joins. Joins are a very powerful tool to merge data contained into two different tables. Suppose you have two tables, people and cars. Create table people, age int, not null. Name varchar 20, not null, primary key. Create table cars. Brand varchar 20, not null. Model varchar 20, not null. Owner varchar 20, not null, primary key. We add some data, insert into people values 37 Joe, insert into people values 8 Ruby, insert into cars values Ford Bronco Joe, insert into cars values Ford Mustang Ruby. Now say that we want to correlate the two tables because this police stopped Ruby driving, looks young, and want to know his age from their database. We can create a join with this syntax. Select the age from people join cars, on people.name is cars.owner, where cars.model is Mustang. We'll get this result back, age 8. What is happening? We are joining the two tables, cars on two specific columns, name from the people table, and owner from the cars table. Joins are a topic that can grow in complexity because there are many different kinds of joins that you can use to do fancier things with multiple tables. 15. Removing duplicates using distinct. Sometimes you want to filter duplicates values in a table. For example, say you have the following schema. Create table people, parentheses, name varchar 20, and we add entries to this table. We have lots of join apparently. Insert into people values. Joanna, Roxanne, Paul, Joe. If you run the query, select pointer from people. We get all the duplicates. Name, Joanna, Roxanne, Paul, Joe. Adding the distinct keyword filters out the duplicates. Selecting distinct pointer from people. Name, Joanna, Roxanne, Paul. Point 16, using wildcards. With using you can select rows from a table using wildcards. For example, you have this schema in this data. Create table people, name varchar 20, insert into people values. Joe, John, Johanna, Zoe. This query will return the first 3 rows as they all start with Joe. Select pointer from people where name like Joe. Looking for roles like Joe, you only select John and Johanna. Select pointer from people where named like John. Notice I use the percent sign to match multiple characters. You can also use the underscore sign to match one character, so you can package Joe and Zoe using select times from people where named like underscore or E. "17. Indexes. When the data in the database table becomes a lot, the database could start becoming slow and doing some operations. To prevent this, you can add indexes. When you try to look for specific information in a book, you look at the index and jump to the page it tells you. That's pretty similar to what indexes do in databases. It's a way to tell the database what to optimize for when looking for data. Indexes start to become a rather advanced topic, especially when relations between tables get complex. To put things simply, which indexes to add does not depend on the schema, but rather on the keys you do. For example, if you have a user's table with a name field, and you frequently get that value and select, then name should be an index. You can create an index using the syntax. Create index name on user's name. The same goes for rows using in where clauses on big tables. Indexes can improve performance at the cost, however, they make selection faster, but slow down insertions and updates. Also, they increase disk space usage. As with everything, it's a trade-off, and the performance benefits must be carefully measured. The good thing is you can add and remove indexes when you run into performance issues. So it's not something you have to optimize for in the beginning. Point 18, aggregation data. You can ask the database to perform a few operations on the data stored in a table. For example, doing a sum of the values of a numeric field or calculating the average. For example, let's take this database schema as sample data. Create table people, name varchar 20, age int. Insert into people values Joe 20, John 30, Johanna 25, Zoe 23. AVG parentheses, calculates average. If you want to get the average age of those people, you can do this. Select AVG age from people. And here's the result. AVG is 24.5. You typically alias the result of the function to name of your choosing. Select AVG age as average from people. Age 24.5. In the same vein, sum parentheses calculates the sum, select sum, age as total from people. Now what is this, man? I dropped my cigarette. Select sum age as total from people. Total 98. Use max or min to get the maximum or minimum value. Select max age, minimum age from people. Max, min, max 30, min 20. 19. Grouping data. You can group data using the group by clause. Select from people. Group by the problems. For example, let's take the database schema and sample data. Create table people. Name varchar 20. Department varchar 20. Age int. insert into people values. Joe sales 20, John sales 30, John IT 25, IT 0, IT 23. We want to get the average age of each department. Here's how we can do that. Select department AVG as total from people group by department. And here's the result. Department total sales 25, IT 24. Point 20. Limit and offset. You can limit the number of rows achieved. This is not in the standard SQL. And each database does this differently. MySQL and PostgresQL use limit. Select terms from people order by name limit 10. And you can set an offset to return in this case. Rows from 11 to 20. Select pointer from people order by name limit 10. Offset 10. Comments. You can add comments to SQL queries using 2 hyphens at the beginning of a line. Just a test, select pointer from people or use / *** to comment a portion of SQL inside the line or to add multiple lines. Comments. Select pointer from / pointer / people. Select from test people. I think we've read everything. That person has not written so much. It's not a real big book like this, but I got a lot of books, of those small books. You got the Swift handbook, the Svelte handbook, the SQL handbook, what we just read, React handbook, Python handbook, PHP handbook, Node handbook, Next handbook, Laravel handbook PDF, JS handbook PDF, HTML handbook, GP handbook, Express handbook, CSS handbook, CLI handbook, C handbook. See what we've got. We have recorded for half an hour. That's quite a lot.